Dear students, now we are going to solve important problems in single step matching. The important formulas are reflection coefficient K is equal to ZR minus Z0 divided by ZR plus Z0. ZR represents the receiving end impedance, Z0 is the characteristics impedance. Here K is equal to the modulus of K with the phase phi. Okay. Wavelength lambda is equal to c by f. C is the velocity of light. Okay. So next, the position of the stub. This is very important. Okay. The location of the stub, it is given as d or ls, that is equal to lambda by 2 pi tan inverse of square root of zr by z0. Okay. So this can also be calculated using the reflection coefficient. So here ls is equal to lambda by 4 pi, phi plus pi minus cos inverse of modulus of k. So this formula is very important. Okay. The next one is the length of the stub. So LT is equal to lambda by 2 pi tan inverse of square root of ZR Z0 divided by ZR minus Z0. This can also be calculated using coefficient. So that formula is lambda by 2 pi tan inverse of square root of 1 plus k square divided by 2 into modulus of k. So these two parameters are very important to design step matching. Okay. Here the first problem. A dipole antenna whose input impedance is 100 ohm to be matched at a frequency of 100 MHz to a transmission line having the characteristics impedance of 600 ohm by means of short-circuited stub. We are going to determine the location and length of the stub. So first we have to write the given data. So in this one, at matched condition, the input impedance is equal to the receiving end impedance. So we can write the receiving end impedance ZR is equal to 100 ohm. The characteristics impedance is 600 ohm. Frequency is equal to 100 MHz. Okay. So in the solution part, first we have to find out the wavelength. Lambda is equal to c by f. So here c value is 3 into 10 to the power 8. That is the velocity of light divided by f value is what? 100 megahertz. So mega means what? 10 to the power 6. From this we can get the wavelength lambda is equal to 3 meter. Okay. So next we are going to find out the location of the stub. For that we can use the formula in terms of impedance. Okay. Because the given data are only the real terms. Okay. In that case we can use this formula. The location of the stub ls is equal to lambda by 2 pi tan inverse of square root of zr by z0. Substitute the values of lambda, zr, z0 here. Then we can get 3 by 2 pi tan inverse of square root of 100 by 600. So tan inverse of square root of 1 by 6, its value is 22.2 degree. So here we are going to find out the location, correct? So in that case we have to convert this degree into radian. For that we can multiply the degree with the value pi by 180 degree. Then we can get the location of the stub as 0.185 meter. Okay. Next we are going to find out the length of the stub. Here the formula in terms of impedance is used. LT is equal to lambda by 2 pi tan inverse of square root of Z0 ZR divided by ZR minus Z0. We can substitute the values of lambda as 3 meter, Z0 value as 600, ZR value as 100. Okay. After substituting these values, we can get 3 by 2 pi tan inverse of 244.95 divided by minus 5. So here tan inverse of this value is minus 26.1 degree. Since the angle is in negative sign, we have to subtract this angle from 180 degree. Okay. So here it is equal to what? 3 by 2 pi 180 degree minus 26.1 degree is equal to 153.9 degree. Okay. After that we have to convert this degree into radians. Then we can get the value as 3 by 2 pi into 153.9 degree multiplied with the value pi by 180 degree. Then we can get the answer as the length of the stub is equal to 1.28 meter. Do you all understand this one? The next problem, a load 50 plus J100 ohm is connected across a 50 ohm line. Design a short-circuited stub to provide matching between the source impedance and the load impedance at a signal frequency 30 megahertz. Okay. So in this problem, first we have to write the given data Z0, that is the characteristics impedance of the line 50 ohm. The receiving end impedance, that is the load impedance, is equal to 50 plus J100 ohm. Frequency F is equal to 30 megahertz. Okay. So in the solution part, first we have to find out the wavelength lambda, that is equal to C by F. So here 3 into 10 to the power 8 divided by the frequency is what? 30 into 10 to the power 6. We can get the lambda value as 10 meter. So here the load impedance is given as a complex term. So for that we can use the formula in terms of reflection coefficient. Okay. So here reflection coefficient K is equal to ZR minus Z0 divided by ZR plus Z0. Then we can substitute the values of ZR and Z0 here. So 50 plus J100 minus 50 divided by 50 plus J100 plus 50. Then we can get J100 divided by 100 plus J100. So it is in rectangular form. We have to convert this into polar form. So here we can use the method. What is that? We have to press shift plus symbol. Then you can see polar with the open bracket. We have to give the real term first. For the numerator, its value is what? 0, comma, the imaginary term is what? 100. Then we can press equal sign. We can get the value as 100. Okay. For getting the phase, we can use the technique alpha continuously. Okay. Alpha plus tan. Then press equal. We can get the angle as 90 degree. Okay. Similarly, we can get the value for this denominator. That value is 141.4 with phase 45 degree. So after that we can divide these two values. Okay. So 100 divided by 141.4 is equal to 0.707. 90 minus 45 is 45 degree. So from this, the magnitude value is 0.707. The phase value phi is equal to 45 degree. This 45 can be written as pi by 4. Do you all understand this one? Location of the stub. Here the formula is LS is equal to lambda by 4 pi. Phi plus pi minus cos inverse k. So substitute the values of lambda, phi and k. Lambda value is 10. Phi value is pi by 4, k value is 0.707. Then we can simplify this term. We can get the answer as cos inverse of 0.707 is 45 degree. Substitute that value as pi by 4. So here the answer is 2.5 meter. Okay. Here the last problem. A ultra high frequency lossless transmission line working at 1 GHz is connected to an unmatched line producing a reflection coefficient of 0.5 into 0.866 plus j 0.5. Calculate the length and position of the stub used to match the line. So it is very important one. Okay, so in this problem they have directly given the reflection coefficient. Okay, we are going to find out the length and position of the stub here. So k value is equal to 0.5 into 0.866 plus j 0.5. F is equal to 1 gigahertz. Okay. So here giga is nothing but what? 10 to the power plus 9. Okay. So first we have to find out the k value. For that we can multiply in this 0.5 inside this complex term. We can get k is equal to 0.433 plus j 0.25. So again we have to convert this rectangular into polar form. K is equal to 0.5 with angle 30 degree. So here lambda is equal to C by F. We can get the value as 0.3 meter. Okay. So now we have obtained the modulus of K value is equal to 0.5. That is the magnitude value. Phi is equal to 30 degree. That is equal to pi by 6. Lambda is equal to 0.3 meter. So next we are going to find out the position of the step using the formula lambda by 4 pi 5 plus pi minus cos inverse k. Substitute those values here. Then we can get 0.3 by 4 pi, pi by 6 plus pi. Here cos inverse of 0.5 is what? 60 degree. That is nothing but pi by 3. We can get the value like this, 0.3 by 4 pi into 5 by 6. So we can simplify this term. Then the answer is 0.625 meter. That is the position of the step. Okay. So next we are going to find out the length of the step. The formula is what? Lambda by 2 pi tan inverse of square root of 1 plus k squared by 2 into k. So here we have to consider only the magnitude. Okay. Then we can substitute the values of lambda and k here. Okay. Then we can get the answer as 0.32 pi. The angle of this tan inverse of 0.866 is 40.8925 degree. So we have to convert this degree into radian by multiplying pi by 180 degree with this. So here the answer is 3.4 centimeter.